Hello, calculus family, and welcome to a video about integration by parts, another technique of integration. One way I like to think about integration by parts is what do you do when one U sub isn't good enough? You kind of do two of them. And that's what integration by parts really is. So, in our order of doing things, we did U subs first, and now we're doing integration by parts second. Now, when we did integration by U substitution, we often would say that U is like the thing in parentheses, and then du should replace a lot of the other stuff in your integrand. How did you know when to do U subs? When you had a product or a quotient you couldn't get rid of, but one part was kind of the derivative of another part. All right, and that's how U subs worked. There are lots of other times that you have products or quotients that you can't get rid of. And if a U substitution isn't going to work for it, then we need something else to do. Now, I don't want you to write this down, but I want to give you an example. So let's say I wanted to integrate x times e to the x. And you said, all right, well, I have x times e to the x. That's a product I can't get rid of. Let's try a U sub. Don't write this down. And we'll say, well, U is the thing in parentheses. I guess maybe x is in parentheses. And then the derivative of x would be 1. So this would be the integral of u e to the u du, and all I've done is just rewrite x as a u's and nothing got any simpler. Okay, well, maybe I didn't do that right. Maybe instead of x being my u, I could let u be e to the x. Okay, well, then du would be the derivative of e to the x, which is still e to the x, didn't go anywhere. And then, I don't, yuck. I have an e to the x here and an e to the x there. And no, this u sub isn't really going to replace anything. I don't think this is going to work out so well for me. So this is an example of when you have a product that you can't get rid of and a u sub isn't quite good enough. We need another strategy. And one of those strategies is integration by parts. Now, integration by parts comes with its own formula. I'm not going to prove where the formula came from right now. I'll get to that later once you've seen how it works. But what you really need to know is that integration by parts says that the integral of u dv equals u times v minus the integral of v du. All right, what this formula really does for us is it says if you're trying to integrate a product, and that product being u times dv, the formula takes half of the antiderivative for you and then leaves you another antiderivative to do on your own. Okay, so the formula kind of takes care of half of your work, and then you hopefully will have a simpler integral to solve when you're done. All right. Now, what that means, though, is that you need to separate your original integrand into a u part and a dv part. So if I come down here to this one, I have the integral of x times e to the x. So one option is that I call x u and then the rest of it dv. Okay. Or if I wanted, I could call e to the x u and then x dx dv. Well, how do you choose? Well, the good news is there is a method to kind of start how to choose it. All right. And it's a quirky little acronym, LIATE. The thing you want to choose as your U part should be a logarithm if there is one. If there isn't one, choose an inverse trig function. If there's not one of those, choose an algebraic function, and by algebraic I mean x to a numerical power. If there's not one of those, pick a trig function, and if there's not one of those, pick the exponential function to be your u. And what you're going to do is you're going to go through and find the first one that you see. All right, so we want to use LIATE. And if you don't think you can remember that, I sing it in a song that one of my students came up with years ago. And I don't know why, but his little melody always sticks in my head. It's LIATE, kind of sung like a Gregorian monk. I don't know why, that's just what's stuck in our heads. So LIATE, that's what you're looking for, okay? All right, Mrs. Vibber, let's do an integral, shall we? So I need to integrate x times e to the x, LIATE, L, logs. Nope, don't have one of those. I, inverse trig. Nope, don't have one of those. A, algebraic, x to a numerical power. I do have one of those. So U is going to be x. And then everything else that's left over automatically becomes dv. So dv is e to the x dx. So you choose u, then everything else becomes dv. Now I need to calculate du and v. Well, if u is x, then the derivative of u is 1 dx. And if dv is e to the x dx, then the antiderivative of e to the x dx is e to the x. Okay, so I'm going to choose u, write down the rest of it as dv, and then solve for v and du based on those setups. Now, the integration by parts formula says the integral of u dv equals u times v minus the integral of v du. And I do not have a Gregorian chant for that. If you want to come up with one, let me know. All right, so now I'm going to substitute everything in. So the integral of u x dv e to the x dx equals u times v. Okay, so that's x e to the x minus the integral of v e to the x du 1 dx. And really, I don't need to write the 1, okay? So the antiderivative of x e to the x dx has an x e to the x in it and also whatever the answer to that integral is. Well, x e to the x is just going to stay by itself, and now I need to take the antiderivative of e to the x dx. Well, the antiderivative of e to the x is just e to the x plus c. And that's our final answer. Okay, so what did we just find out? We found out that the antiderivative of x e to the x is x e to the x minus e to the x. And if you don't believe me, one of the great things about integrals is even though they don't have rules, they can always be checked. So let's see if the derivative of this is our integrand. So the derivative of x e to the x is a product. So I've got the first times the derivative of the second plus the second times the derivative of the first minus the derivative of e to the x is e to the x, and the derivative of a constant is 0. So I have x e to the x plus e to the x minus e to the x. Well, these add to 0, so I just get x e to the x. That's what I started with. I did the right thing. More integraling, less talking. Let's try it again. What if instead of x e to the x, I had x times cosine x? Okay, well, if I try to u sub, the only u that would really make any sense would be u equals x. And if u equals x, you're just writing everything with a different alphabet, and that's not helpful. So I have a product here that I definitely can't get rid of. So if I want to evaluate this integral, I'm going to do LIATE. So L logs, nope. I inverse trig, now I have regular trig. A, x to a power. I have one of those. So that's going to be u, and the rest of this is going to be dv. So u is going to be x. dv is going to be cosine x dx. My face is close to that camera, huh? And then if I want to figure out everything else, I need to take the derivative of u, take the antiderivative of cosine. Whose derivative is cosine? Oh, yeah, that's sine. So the integral of u dv equals u times v minus the integral of v du. All right, so the antiderivative of x cosine x starts with x sine x minus the integral of sine x. And you know what? I can evaluate that second integral. So this is going to be x sine x. And then whose derivative is sine? That would be negative cosine. So this will become plus cosine x plus c. The antiderivative of x cosine x is x sine x plus cosine x plus c. Now let's check it here. So if I were going to check our work here and take the derivative of x sine x is a product rule. The first times the derivative of the second plus the second times the derivative of the first plus the derivative of cosine x, which is negative sine x, and the derivative of c would be 0. Those add to 0, and I just get x cosine x, which is what I wanted. Now seems like a good point to say, you know what, this integration by parts formula didn't just appear out of thin air. It appeared from the product rule. If you'll notice, each time we did these derivatives to check our antiderivative, we were doing the product rule every time. So let's talk about that for a second. So if I have a product, let's call it u times v, and I were to take the derivative of that product, if u and v are functions of x, then the derivative of u times v is going to be the first times the derivative of the second plus the second times the derivative of the first. Okay, and to simplify this, all right, just for a second, to simplify this, I'm going to write that as d dx of u times v equals u dv plus v du. Okay, fine. Well, how about I rearrange this a little bit? How about I subtract v du from both sides, just because I feel like it? All right, well, fine. Then that's going to be d dx of u times v minus v du equals u dv. Okay. Well, another thing is I can subtract from both sides. I can also integrate both sides. I'm going to integrate this side. I'm going to integrate that side. And one of the rules of integration is if you integrate a sum or a difference, then the integral can be separated into two integrals, the integral of the first part and the integral of the second part. Well, the integral of a derivative, integrals and derivatives are opposites. So when I integrate and differentiate, they effectively cancel out. So I'm left with just u times v minus the integral of v du. Hey, wait a second. There it is. That's the integration by parts formula. The integration by parts formula came from using the product rule and then integrating both sides. Okay, so integration by parts is really just the backwards power rule, and U substitution, kind of, is really a backwards chain rule. Okay, all right, so I'm hoping that that makes sense. Let's move on here to do a couple more. Now, one of the things that I forgot to do when I wrote this is I forgot to create one of these with some limits of integration on it. So I'm going to add some limits of integration, let's say to number 4. And let's change number 4 and make that the integral from 1 to 2. So if you can, before we start anything else, put a 1 and a 2 on there. All right. And then let's come up here to number 3. So it says evaluate the integral of x squared sine x dx. Okay, so I have a product I can't get rid of. And one of these pieces is definitely not the derivative of the other, so U subs aren't really going to help me. Let's do integration by parts. Liate. Oh, here's an A. So that's going to be U, and then the rest of this is going to be dv. So U is going to be x squared, dv is going to be sine x dx, which would make du 2x dx. And then v would be negative cosine x. All right. So the integral of u dv equals u times v, u times v, which would be x squared times negative cosine x, minus the integral of v du. Now I'm going to be minus, and there's a negative cosine, so I'm going to turn this into a plus. And then I have v du. Okay. Well, wait a second. Now my v du part is another product. You know what that means? We get to do integration by parts again. Yay! So what I'm going to do is say, wait a second. One integration by parts wasn't enough. Now I got to do it again. That's going to be u, and the rest of that's going to be dv. So u is going to be 2x. dv is going to be cosine x dx, making du2 and making v sine x. Okay, so now I got to be a little careful here. So I still have this negative x squared cosine x plus the integral here is going to be this entire thing I'm about to write. Get my face out of the way here. The integral of u dv equals u times v minus the integral of v du. Okay. And I can evaluate this antiderivative. So I have negative x squared cosine x plus 2x sine x. And the antiderivative of 2 sine x would be negative 2 cosine x. So that's going to be a plus because I've already got a minus there. 2 cosine x plus c. Whew. What did we just find out? We found out that the antiderivative of x squared sine x is negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. Life isn't fair and integrals don't make sense. Okay, yeah, integrals do make sense, but my point is life isn't fair and integrals aren't always something that you can figure out in your head just by looking at it. All right. Now, I have 2 more examples down here that I am going to do with you. They take a little while, so if you would like to pause the video right now and take a break and come back, you can absolutely do that. I don't want to make a whole other video, so I'm just going to keep rolling with it, but if you need to take a break, please do so. All right. Now, these last 2 are a little bit different because I said that when we have a product or a quotient we can't get rid of, we can try U subs or integration by parts. But when I look at number 4, that's just the integral of ln x dx. I don't have a product or a quotient. Okay, so maybe I can do this without integration by parts. Maybe I just put the wrong question in here. Let's see. The antiderivative of ln x. Wait, we haven't done that before. The other nice thing about integration by parts is integration by parts can be really useful if you have a single thing and you just don't know its antiderivative. You don't need to have a product. So what we do is we kind of fake a product. So we say L-I-A-T-E-L, logarithms. Oh, I have one of those. So U is going to be ln x, and then dv is going to be everything else. Well, everything else is just dx. Fine. Let's see, the derivative of ln x is 1 over x. And the antiderivative of dx, well, wait a minute. The antiderivative of dx is like thinking of the antiderivative of 1 dx. And the antiderivative there would be x. Okay, not a big deal. So what I have here is the integral from 1 to 2 of u dv equals u times v minus the integral of v du. All right, now what do I do with those limits of integration? When we did U subs before, if I did U subs, I needed U bounds. Well, here's the thing. I don't need new bounds. I don't need new limits of integration because I never actually put things in terms of U and V. I just use the U and the V to restructure, but I never put things into terms of that. So this 1 and 2 is going to go here, and it's also going to go right there at the end as a bar because I've already taken half of the antiderivative there. All right. So that's how a definite integral would look. And if I come over here, I still have, let's see, ln x times x from 1 to 2. So that's going to be ln 2 times 2 minus 1 times ln 1. Minus, now let's take the antiderivative over here. Well, x times 1 over x is really just 1, and the antiderivative of 1 is just x, and I'm supposed to evaluate that from 1 to 2. So I have 2 ln 2 minus, well, this is 0, minus 2 minus 1. So this is going to be 2 ln 2 minus 1 is your final answer. What do we think? All right. So you learned two things there. One, that integration by parts can be used when your integrand is just one single piece that you just don't happen to know the antiderivative of. Two, if you're going to do integration by parts on a definite integral, then your limits of integration get stuck at the end of the first part of integration by parts, and they go on that integral at the second part. All right, let's do one more. So what if I wanted to integrate inverse sine x dx? Well, let's see. U, L-I-A-T-E, nope, no logs. I, inverse trig. I have an inverse trig. Let's use it. So this is going to be U equals inverse sine x. And then dv is everything else, and that's just dx, fine. And then du and v, well, the derivative of inverse sine x, of course I've memorized all the derivatives of the inverse trig functions, Mrs. Vibber. You told me to do that, and I've done that. Right? The derivative of inverse sine x is 1 over the square root of 1 minus x squared dx. See it, know it, love it. And then the antiderivative of dx is just x. So the integral of u dv equals u times v. I said it and wrote it backwards just because I want the x in front. U times v minus the integral of v du. Now I've got another quotient. Well, what am I going to do with that? Antiderivative of x over the square root of 1 minus x squared? You know what? I don't know what that antiderivative is. But you know what I'm noticing? Is that I have like an inside part of 1 minus x squared, and the derivative of 1 minus x squared would be negative 2x, which is kind of what I got right there. This is integration by parts, and we finish strong with a U substitution, but just like a regular U substitution, not an integration by parts U substitution. So now we're going to do that. So I come over here and I say, all right, I got to evaluate this with a U sub. U is 1 minus x squared. Du would be negative 2x dx. Okay, and I don't need the negative 2x, so I'm going to multiply both sides by negative a half. All right, so then this is going to be x inverse sine x minus negative a half, the integral of u to the negative 1/2 du. Make that a plus over here. So then I have x inverse sine x plus, let's see, 1/2. The antiderivative of u to the negative 1/2 would be add 1 to the power, divide by the new power, plus c. And this was an indefinite integral, so I need to unsub my u. And so this is going to become u to the 1/2, which is 1 minus x squared to the 1/2, which is the square root of 1 minus x squared, plus c. Life isn't fair, folks, and integrals don't make sense. The antiderivative of inverse sine x is x times inverse sine x plus the square root of 1 minus x squared plus c. Why? Because it is. And if you don't trust me, take the derivative of that thing down there using a product rule and a chain rule, and you will find that it ends up equaling inverse sine. Okay, so that's integration by parts in a video. Hopefully it makes a teeny tiny little bit of sense, and everybody is having a wonderful day. I hope you continue to have a really good day. And with that, I'm signing off. See ya.